I want to present something about the current state in Faro 11 about variables and especially about how the AST models variables in the current Faro system. This came kind of out of an email. The idea to do this exact setup of the presentation came out of an email at the beginning of the month that I saw after coming back from holiday, where someone asked, I would like to color variables differently in the syntax highlighter. And someone said, yeah, the syntax highlighter that works with the AST, but I know the AST doesn't know about different variables. It only knows it's a variable. And so I thought, yes, that's true, but we can actually know more about variables. And I wanted to explain how this actually works in the current system. So the talk has kind of 3 parts. I want to first explain you a bit about the AST. That's nothing new. It's what we do since some years. Then I want to explain you about variables in the system from another perspective, and at the end put everything together and into one system. So the first thing is the AST, as most of you, I guess, know. AST means abstract syntax tree. This is a tree representation of a method that encodes the syntax of your Smalltalk code. Our implementation is based on the one from the refactoring browser, so that means it's a fairly high-level representation that comes from the tooling world, not from the compilation world. And all the tools in Faro are now using that. So we spent, over the last years, I think I have some slides later about that, quite some effort to actually not have our own representation for every tool, but we use this one AST for everything. And it's actually relatively simplistic because Smalltalk is a simple language. So that means we have just a handful of classes that model different language constructs. And the most important ones, there are some more, but the most important ones are AB method node, that's the root. Then we have variable node, this is the variable, and that's the topic of this presentation. We have, for example, assignment node, where then the left side is the variable, the right side another expression. Message node for message sense, which is the most important operation that we do, and the return node to return. It's kind of the most important nodes that we have. And if you want to look at it in your own image, it's actually quite simple. You can just use the compiler, for example, and ask it, please pass me this method, and it will this piece of text into a method, and then it will return to you an AST, an AB method node that actually then, as you can see here, then has the structure of your code. The inspector that you see, so this tool here, has actually a nice special inspector. This is this tree form that shows you only the important, only the node classes themselves if you're interested in the structure of the method and not everything. So, as I said, our tools use that. As it comes from the refactoring browser, we of course use it for refactoring, so the original user is still there. Then we added something that actually the breakpoints are using the AST directly instead of manipulating bytecode, which is an interesting thing. We changed the syntax highlighter to not have its own representation. So at the beginning, we had our own parser just for the syntax highlighter. This now is just a standard visitor on the refactoring browser, AST. Code completion uses it. For example, the tools, for example, if you have in the code browser, there's a special menu that actually shows you only operations that are valid on this AST node. The most complex user, of course, is the compiler, which for one is kind of the source of the AST, the first half of the compiler. So that means we start with source code at the beginning, and then we use RB parser to create an AST, and then as we will later see, we do semantic analysis, we get an annotated AST, and the annotated AST is created into some intermediate representation, and from there we make the bytecode. What is interesting is that the compiler uses the same AST than the tools. So this is kind of interesting because at the beginning, people thought that you need different representation for the different things, so that, for example, the compiler would need a more low-level representation than the refactoring browser, or that the syntax highlighter needs another representation because it needs to know, for example, which kinds of variable it uses and things like that. But it turned out that we can, louder? That we can actually use the same AST for everything. And one of the reasons is how we actually model the variables in the AST. So if you would just look at point x. So if you have the method in hand, you can actually just send AST, the message AST to the method, to the compiled method, and it will return to you an AST for that method. And here in point x, you can see that it actually has just a return and then the RB variable node inside. So this is how variables look like on the AST. So it's just that it uses RB variable node. What is interesting is that if you then want to use it for something, you need to actually know more than that it's just an RB variable. As you think, RB variable node means this is just a variable with name x. But if you want to do something with it in tools, so here as an example for the syntax highlighter, you actually need to be able to know more about the variable. So here the syntax highlighter, as you can see, it uses some kind of symbol that then is looked up in a color table to color the AST. And so that means we have here methods that actually ask you, is this an argument? Is this a temporal variable? Is this a global variable? Is this a class variable? Is this an instance variable? And it returns true for these cases. So you can actually ask the node, are you a node that references an instance variable? Or are you a node that references a global, that is a global variable? Yeah?
Just from the syntax parsing, this information is not available. You need the binding or
Exactly, that's what I want to explain. So I want to explain why this is more complex than or how it is actually done. So, and that's the next slide. So on the level of the AST, as you saw, it's just RB variable node x. We have no idea what that is. So every use of the variable on the AST gets even its own instance of a node named x, because the AST needs to model the structure. So that means you need a new instance because you have another parent of the node. So that means every use, the definition itself, every read, every write, so left-hand side of the assignment, is a new instance RB variable node. And we know nothing about it. We only know this is a variable named A, which is actually why it's called syntax tree. Because on the level of the syntax of the language, the only thing that is in the syntax is that this is a variable. So the fact that it's a global variable or a temporal variable is not part of the syntax. There's, of course, a syntax to define a temporal variable, but the variable x assigned to 5 is an assignment to a variable, and the grammar doesn't know anything about which kind of variable it is. And in addition, you could say, yeah, no problem, I will just look where this variable is. I mean, I know the method, so let's do that. It's actually not that simple, because variables with the same name actually can be different variables, because you have shadowing. So you can make a temp that shadows an instance variable. In our system, we decided to actually interactively not allow that, because in Smalltalk there's no need to do that, because it's just annoying to understand the code if you shadow variables. But if you load code non-interactively, so if you file in a change set, this can happen, that you get shadowed variables, and the compiler does, of course, compile it correctly. So you can have a temp that shadows an instance variable without a problem, or a block argument that shadows a temp. And you need to deal with that. And it's clear that this means that just ad hoc look for the variable doesn't really work. I mean, you could say, no problem, I will just first look if there's an instance variable with that name, and if not, then I know if it's a lowercase letter, it's a temp. Nah, that is not really a good idea. So what do we actually do to solve this problem? So what we do is that we keep the AST as it is. So that means we keep the fact that every use of a variable has its own instance. We need that because the structure is encoded with that. I mean, but what we do is that we actually annotate every variable node with semantic information, and that is done by the name analysis phase of the compiler. It is done technically by actually having a scope, which is a dictionary for for the method itself, for every block that is created. So that means if you have a scope for the method, you have a scope for the block, and if inside the block is another block, you have a scope for that block. And every definition of a variable puts an entry into that scope. The scopes know always their parent scope, And that means that we can just ask the current scope for the name of the variable, and it just looks in its own dictionary if the variable is there. If not, it goes to the parent scope, and the parent scope of the method is then the class, and the parent of the class scope is then the global scope, Smalltalk globals, and this way you can look up variables quite easily. But it, of course, means in the next step, or if you step back and think about it again, that you need actually a class hierarchy and objects that model variables that are independent of the AST, but that are objects that are objects describing the variable. So that means that you need a class describing instance variables, you need a class describing temporary variables, a class describing global variables, and of course, as a good object-oriented programmer, you actually make a hierarchy out of that. And this you would call semantic variable. And this is what the compiler actually used to have. So it had its own hierarchy of scopes and semantic variables. If you now, and that means that if you look at that, at the semantic variable, what it has a name and a scope, more or less, and then methods to do whatever you want to do, for example, for the compiler, which I think I mentioned later. So if you look at that now in the system, it has to be like that. I mean, we need that, and right now, if you inspect it, you see actually here that, so we inspect here again point x, the AST of, or we inspect the AST, and then we go to the tree, we go down to the RB variable node, so you see here it's RB variable node, and then you see that we do have here something called variable, which is actually the annotation that gives semantic meaning to that node. And this is actually then used by all the tools that need to know this difference. So for example, the example that we saw before, where we have these check methods like every variable node, are you standing in for an instance variable, or are you a global node? These one actually delegate to this annotation and ask this annotation, are you an instance variable, semantic variable or not? Another thing is, as these semantic variables are part of the compiler, one of the things that they do is they actually implement all the code for the compiler. So that means the compiler does itself not know what to do for emitting read and write code of variables, but the compiler just says, I will delegate that to the semantic variable, and this one then knows how to read and write itself. So here, as the example that I show, this is for instance variables. So the compiler would actually then, if it wants to store an instance variable, it actually would delegate to the semantic variable describing instance variables and call emit store there, hand over the method builder instance that it has, which is like a stream object where you call methods on to create bytecode, and this one then is just method builder store instance variable. And index is the state that the semantic variable knows, because that is what an instance variable is. It knows its index. And so we need, if we want to build a compiler like this, we need for every kind of variable, we need to have an emit store, emit value. So we need that for globals, for instance variables, and for temps. And for temps, this is actually the most complex, the most complex case, because compiling, reading, and writing temps that are actually coming from a closure is more complex than you think. And I will not go into details there too much. So that was the view of the AST. So what we have seen, AST, abstract syntax tree, that means it's a tree representation of method, but it actually, on its own, the variables do not know anything about them. They only know they are variable of a certain name, and to make it useful for tools, we need to semantically annotate the AST, which we do. So now we know about the AST point of view of everything. And this is actually like that since the beginning of Faro, I think. So the Opal compiler uses this notion from the start, because the idea was there, we use the RB AST, we don't want to change the AST into something that is more than syntax. So we actually had a version in the middle where we actually added subclasses or every variable node that then every instance variable node, every temp node, and that turned out to be not really a good idea. But for code generation, we always had semantic variables, and so yeah. So this is what we need. If we now step back and we go outside of the compiler, so compiler we completely ignore in the AST. Now let's look at these variables from the reflective point of view. So not as infrastructure for tools or for something that is used for code generation, but more from a language model point of view. And so we are now in part 2, where we look at variables from that point of view. And first, to kind of understand it better, we need to look at how variables are actually originally in Smalltalk. So I think I need to check how much time I have. Oh yeah, it should work. So in Smalltalk 80, originally, variables are actually quite simplistic, partly because, of course, this needed to run, you couldn't model too much because memory is sparse. So for example, instance variables are defined by a class. The class has just an array of names. You can read them reflectively by calling instvar named or instvar add. Instance variables have an offset in the object, and that's the same offset then in the list of variables that you have in the class. And the order, yeah. So and if you have a class hierarchy, then of course you need to always take into account the superclass variables too. So if you have two variables in a class, the superclass variables are part of the variables of the instance. So yeah. So in the end, quite simple. Temporary variables in Smalltalk 80. Are defined by a method or block.
More down. Because with this here.
I'm stretching.
You can put it here.
Ah, yes.
Sorry. I'm sorry. Something like that. Okay. Yeah. Sorry.
Yeah, so then there are temporary variables which are part of a method. Arguments are temporary variables too in the model that we have. You can read them with temp named and temp named put from the context. And as I said, with closures, the actual implementation is much more complex than you ever would think. We have globals. They are entries in the Smalltalk globals dictionary. They contain these entries, so the association actually contains the value of the global, and you can read them either from the global dictionary using normal dictionary protocol like add and add put, or you can get out the association and value to it to get the value. And class variables and pool variables are implemented the same, only that they are from different dictionaries, so not from the global dictionary, but from a dictionary from the class. If you now think about that we always say everything is an object, then it's clear that for variables, not really. So for the globals, this case, it's actually the one where you could argue that it's already kind of okay, because there is an object that represents a global variable, and that's the binding, so the association in the Smalltalk globals dictionary. And you can even ask for it. So if you say object binding, you get back an association that models the global variable. But the API is a bit strange, so you have only value and value, and yeah. And the class actually just defines the name of class variables, so it's not really that great. Instance variables, it's worse, as we said, it's just a list of names. There's no object that represents the variable at all. It's just a name in a list, nothing else. And everyone just accesses it by offset. And temporary variables are not modeled at all, because in the compiled method object does not even store the names of the temporary variables. So if you want to know anything about variables on the level of the method, you need to actually either compile your source code or decompile. No, decompiling doesn't work. So you need the source code to reason about temporary variables because the only place where the name is stored is the source code. And reflective read is actually quite difficult with that model. And if you look at the old implementations, or if you go back to Faro 7, I guess, then you can look at the kind of metadata that the compiler needs to create to read temps. It's quite complex. So we ask ourselves, why can we not do better? And over some iterations, we actually now have a hierarchy of variable in the system. So there's a superclass, which is called variable, and every kind of variable in the system has its own class. So that means there is something called little variable, which is a superclass of class variable, global variable, undeclared, and the workspace variable. Then we have local variable, which is a superclass of argument and temporary variable. So on that level, we actually do distinguish temps and arguments. And we have self, super, and this context as their own implementation. And slot is the superclass of all instance variable-like variables. And that is actually quite nice because now we have an object for every variable in the system, and we have a meta API for these. So for example, if you want to ask, if you have a class, you can ask it, give me all the variables that you define, and then you can send messages to that objects to do something else. So for example, using methods. So if you get a variable object, regardless of which variable object, you can ask using methods, and this will return all methods that use this variable in some way. So you can say, for example, point, you get the variable for point x, and then you say using methods, and it will give you all methods that access point x. Another API that is important, especially for debugging tools, is that you can actually read from variables. So for instance variables, this uses the API read and write. So that means you first get from somewhere the object that represent your variable. So in this case, we say point instance variables first, which gives you the point x. And then we can say read in 5 and 4, and then it will return 5. Or we could do with write 2, we could change this. The nice thing is that these meta objects actually read and write without sending a message to the object. So they use the primitives that we have in the system to change state without having to send another message to the instance. As such, they are real meta objects for the instance with regard to reading and writing state. For globals, we actually keep the API that we can, if you have a class, we can just ask binding, and it will return to us the global variable object. And this one, we can ask for its class, for example, and it would get global variable, or we can say read, and it would read the global variable. Or we can say write, and we could store a new value inside of that. We keep the association API for global variables, and this allows us to just keep them like before. So they are actually associations in the global Smalltalk globals dictionary, but they are not associations anymore. They just implement the associations API. But it allows us now to actually use the standard API of variables on these objects. So we can say object binding using methods, and it would give you back all methods in the system that actually you read object in any form. For temporary variables, it's a little bit different because we cannot afford to instantiate all temporary variables. So we cannot have one instance for every defined temp in the system because there are quite a lot. But we can deal with them the same than we deal with the AST itself. So for the temporary variables, they are created when the AST is created, and they are gauge collected when the AST is not needed anymore. And this means that it's quite natural to work with them because they have the same lifetime. So when a tool wants to do something with the AST, it actually at that point has all these variables instantiated, and as soon as the AST is not needed anymore, they all are garbage collected. But we have some API on compiled methods, so we can, for example, ask a temporary variable named on any compiled method, and it will return you an instance of that variable and create it at that point so that you can actually do something with it.
Marcus,
Yeah.
so with temporaries, you need to bind them to a scope, temporary meta object, temporary variable meta object. You need to bind it to a scope.
So
The values.
they are always, so the temporary variables are always, repeater. So if the temporary variables are bind to a scope, yes. So the AST itself, the name analysis of the AST will create a scope for every, for the method itself and for every block. And then it will allocate the temporary variable object and put it into the scope. So that happens automatically when you do name analysis. So if you ask for an AST, you get back an AST with the instantiated temporary variables objects ready to use. And then we have some methods that you can actually ask for them independently. But I think this one then instantiates the AST in the back, so to make sure that these are the same objects. What we then did is that we actually, so every of these variables have a scope attached, as we said, like the scope for blocks or for the method. But for instance variables, the scope is the class. And for global variables, the scope is Smalltalk globals, of course. And with that, we actually have, we can actually look up variables with lookup var. So for example, if you, if you do this, you get the scope of the slot x and point is actually point class, but the outer scope of the point class is Smalltalk globals. And what we can do now is we can actually look up those variables using lookup var from every scope that we have in the system. So if you are in a method scope and you look up var object, it would go up until to the globals and it returns you the object. And we added that to context too, so we have a lookup var on context and you can look up any object there. The reason for that is that this allows us to very easily read variables in the debugger. So you can just look up any name, you get back a variable, and then you can call read in context, and you can read the variable, regardless of which variable it is. So every variable can read itself in the current context. Temps need the context, everyone else, so instances, they get the object from the context and read themselves in the object, and globals, of course, just ignore the context. But this actually allows us to simplify the debugger variable read a lot, and it allows it in another step to actually wrap those variables into for doits, to wrap them actually in a doit variable, and this allows us to have nice names for doits, which I actually want to show in the show us your project, because it needs a bit of explanation why this is nice. But it means that now there is no odd thing that you get a doit method where you have like temp at this context, temp at 5 or something like that. But that I will show in the show us your project. So if we put it all together, because this was now talking about variables from a reflective point of view. So now what we saw already at the end of this idea of reflective variables is that we have the notion of a scope. And if we have a notion of a scope and lookup var, then these reflective variables actually have all the features that we need for these semantic variables that we had at the beginning. So that means what we can do now is we can actually, instead of having our own hierarchy as part of the compiler, which models semantic knowledge about variables, we can actually use the same hierarchy for this. So in Faro, since I think Faro 10, since Faro 10, the hierarchy that we use to give semantic meaning to the AST variables is the same objects than the objects that model variables from the reflective point of view. So that means question?
Where does pool variables fit in this scoping? Pool variables, where do they fit in this?
Pool variables are, so in Faro, a pool is always a subclass of pool dictionary, of shared pool. And so that means pool variables are always class variables of that class. And we added an API that you can actually detect that. So that means you get it's a class variable, but you can ask, are you from a pool? And then it says true. Which pool are you from? And it gives you so there is an API to discover that all.
But you can do lookup variable in any scope.
Yeah, you can, if you have the class that implements your pool, you just say lookup var for the name and you get back the, or you use the reflective API that we added already a long time ago, like class variable named, then you get back the class variable of the pool, and this is the same variable then later. For pools, it's always a question. So right now it's a bit simplistic because it really just gives you the, and I once wondered if we should wrap them so that they are pool variable, that there's an explicit pool variable subclass, but for now it works like this nicely. It could, yeah, if we find use cases where it needs a better model, we can easily do that. So yeah, so with this, so what it now means is that the problem that we had at the beginning, that the AST needs semantic variables, we can now solve using this hierarchy. And that means that this is now all integrated in one model. So for example, if you, yeah, this is what we already saw. We can ask for a scope of point and we get back the class. We can look up var x in point, and we can, which gives you back from kind of like a class as a scope. Is the same as if you say slot named. You get back exactly the same object. Or you can even go to a method x. You go until you find the first variable node, and then from there you get the annotation, and even that one is the same object than the reflective first class variable that you can get when you ask the class for which variables do you have. So yeah, so that is what we actually got. And I found that interesting because to kind of come from two directions and in the end to have just one hierarchy and one concept. And it means in addition, yeah, what did we get? So I should actually say, so it simplified the whole name analysis question and it reduced the memory footprint of the AST because now we use, every time an instance variable is annotated, it uses the one instance that is already there, for example, or for globals. We get an open compiler. So what used to be classes private to the compiler are now classes of the reflective model. And this means that you can actually define your own kind of variables. And it will work both from a compilation point of view and from a tool point of view. So if you define your own kind of class variable, then it will still work with the inspector because your own kind of class variable will have to implement the code generation point, but it needs to implement the reflective API too. And if you have the two, you can compile and you can use all the tools on them. So that means that you can make your own variables while it's still fully integrated into the reflective model with reflective reading and writing, and all tools will still work. What did I not show? Because I'm already soon out of time. I didn't really go into the detail of how to define your own variables because that is its own discussion, and we had already talks about that in the past. Part of that, fluid class definition. So if you want to define your own kind of class variables and your own kind of instance variables, you need to have, you cannot just give a list of names, but you want to have another way of defining classes. So this is where we worked a lot in Faro 10 and now in 11 to be able to enable fluid class definitions as a feature, which is now available optionally. One thing that I want to show and show us your project is how this enables duets in a nice way, where you have nice variables all the time, as I already mentioned quickly. And then another thing that I didn't go into at all is for reflection. If you want to actually hook into variable read and write, there's now the possibility to work directly with variables instead of having to reason yourself about, this variable, and then I need to find the AST nodes. And so you can now actually put metalinks directly on variables. It's not yet completely finished, the model, but it starts to be quite usable. Yeah, and this is, of course, not my work alone, but it's the work of many people and the result of many discussions. And if you want to join, you're welcome. So this is possible to ask questions on the mailing list, and we can do stuff. Questions? Yeah?
What do you mean by meta links?
Ah, yes. So, yeah, that's maybe, I should have explained. What do I mean by metalink? So metalink is a reflective feature in the system where you can annotate the AST with a meta object, which is called before or after or instead of the original operation, and this is used to implement, for example, the breakpoints. You can think about it as a generalized method wrapper. So a method wrapper that does not only wrap methods, but that can wrap AST nodes, and we actually use a method wrapper implementation on the method level. If it's a primitive, for example, you need to wrap it. There's nothing around it.